In this video, we'll talk mostly about the natural response of second-order differential equations. As with first-order systems, the emphasis will be on assigning physical significance to the coefficients of the differential equation, rather than explicitly solving the equations themselves. As with first-order differential equations in the previous unit, I'll put my second-order differential equations into a standard form before solving them. The advantage of this is that after I've gone through the solution process once, I'll rely on a shortcut approach and use the coefficients of the differential equation to get at least an approximate solution to the differential equation. Linear second-order differential equations can be written in this form. The multiplicative factor on the second derivative is 1. The coefficient multiplying the first derivative is 2 times zeta times omega sub n, and the coefficient multiplying the 0th order derivative is omega sub n squared. The forcing function, or input, is u of t. The reason for writing these coefficients in this form is that the variables zeta and omega n have physical significance. They allow us to directly infer the system behavior. Zeta is called the damping ratio. The damping ratio is a unitless positive number. Omega sub n is called the natural frequency of the system. Omega sub n is also a positive number, and it has units of radians per second. The solution of a second-order differential equation is the superposition of the homogeneous solution and the particular solution. The homogeneous solution is the response of the system with no applied forcing function. It strictly governs the response to initial conditions. The particular solution accounts for the forcing function. Rules for the homogeneous and particular solutions are the same for second-order systems as they were for first-order systems. First, as usual, we'll deal with the homogeneous solution. This solution is also called the natural response or the unforced response. The differential equation governing the homogeneous solution is the same as our original differential equation, except that the forcing function is 0. The natural response of a system is due only to initial conditions. For second-order systems, 2 initial conditions are required. Usually, these are in the form of an initial value of the output, y sub 0, and an initial value of the derivative of the output at time t equals 0, y dot sub 0. Other types of initial conditions are allowable. The only rule is that they have to describe the energy stored in the system at some initial time. Since a second-order system has 2 energy storage elements, 2 initial conditions are necessary to describe the energy stored in those elements. The approach I'll use to find the homogeneous solution will be to guess the form of the solution. Since the solution to a linear differential equation is always in the form of exponentials, I'll assume that the solution is of the form e to the st. I can plug this into the differential equation and solve it to get what is called the characteristic polynomial for the system. For a second-order system in our standard form, this is the characteristic polynomial. The roots of this polynomial are the values of s that go in this solution. If I solve for the roots of this polynomial, this is my result. Since the differential equation is linear, I can use superposition to determine the solution. That means that the total solution is a linear combination of the 2 solutions obtained from the roots of the characteristic polynomial. K1 and K2 are scaling constants that depend on the initial conditions. If I substitute the roots of the characteristic polynomial that I found on my previous slide for S1 and S2 in this equation, the solution looks like this. Both terms contain an e to the negative zeta omega n times t, so I can take that term out and write the solution in this form. This is the result that we'll be working with for the rest of this video. I've gone through this derivation pretty quickly because I don't really care if you remember the derivation. What we'll do next is to use this equation to understand what a second-order system response looks like based on the particular values of zeta and omega n. The effect of those values on the solution is what I think is important for an engineer to know and understand. Now let's talk about how to interpret this equation, especially in terms of the damping ratio zeta. Since zeta and omega n are always positive, this term is a decaying exponential. The time constant of this exponential is zeta times omega n. These terms are a little bit trickier, since their behavior depends upon the value of zeta. If zeta is greater than 1, this term grows exponentially with time since the exponent's positive. This term can grow rapidly if zeta is large, but it will always grow more slowly than this exponent decays. This exponential term decays exponentially with time, so the product of this term and this term should decay relatively rapidly. If zeta is exactly equal to 1, both of these exponents are 0, since 1 squared minus 1 is equal to 0. Since e to the 0th power is just 1, this entire term becomes a constant. Multiplying that constant by this decaying exponential results in a decaying exponential function. If zeta is less than 1, zeta squared minus 1 is a negative number. The square root of a negative number is imaginary, making these two terms complex exponentials. We'll see later that the combination of these two complex exponentials forms a sinusoid, and this function will oscillate with time. This is the source of the oscillations we experience when we play on a swing set. In the next few slides, I'll go over these concepts in a little more detail and introduce some terminology relative to second-order systems. The terms are important since it's common to classify and design second-order systems according to their damping ratio. The first case I talked about was when the damping ratio is greater than 1. This is called an overdamped system. This is my original equation. I've color-coded the three terms in the equation here. For overdamped systems, all three of these terms are exponentials. The blue term is a decaying exponential, the red term is a growing exponential, and the black term is also a decaying exponential. If I multiply these terms out, I get this. I now have two terms, each of which is a product of two exponentials. Since the product of the two exponentials is also an exponential, the natural response contains two exponential functions, each with its own time constant. One of the time constants can be high, since it's a combination of a decaying exponential and a growing exponential, while the other time constant's low, since it's the product of two decaying exponentials. Because of the slowly decaying exponential term, these types of systems can respond slowly. As the damping ratio increases, the decay rate of the function gets slower. This is because the rate at which this term increases is becoming closer and closer to the rate at which this term decreases. In the limit, as the damping ratio goes to infinity, zeta is the same as the square root of zeta squared minus 1. These terms cancel, and this part of the response is a constant. If the damping ratio is exactly 1, the system is said to be critically damped. Again, I've color-coded the terms in the equation to make them easier to keep track of. For a critically damped system, both the red and the black exponential terms are 1, since 1 squared minus 1 is equal to 0 and e to the 0th power is 1. That means that these two terms just become the unknown constants k1 and k2. The response of a critically damped system is then a single exponential. This is a typical shape of a critically damped system response. It looks like the response of a first-order system, but with some differences due to the presence of two initial conditions. The response of a critically damped system will decay more quickly than any overdamped system with the same natural frequency. This figure shows a family of curves with increasing damping ratio in this direction. The blue curve is critically damped. When the damping ratio is less than 1, the solution contains complex exponentials. Before talking about system responses, I want to talk specifically about complex exponentials. Euler's formula says that complex exponentials with opposite signs in the exponent can be combined to form sinusoidal signals. For example, the cosine of omega t is equal to e to the j omega t plus e to the negative j omega t divided by 2. The formula for sine is similar, but with a negative sign here. J indicates an imaginary number. J is equal to the square root of negative 1. I is generally used to indicate square root of negative 1 in physics and mathematics. However, electrical engineers use I for current and J for the square root of negative 1. These are the terms in the second order system response that contain complex exponentials when the damping ratio is less than 1. If zeta is less than 1, zeta squared minus 1 is negative. We can take the negative out of the square root as a j and change the order of these terms to explicitly indicate that these are complex exponentials. This term and this term have opposite signs now. So by Euler's identity, we can write it as combinations of sines and cosine functions. I've used omega sub d in this expression to indicate the frequency of the sinusoids. Omega d is called the damped natural frequency. It's equal to omega n times the square root of 1 minus zeta squared. If the damping ratio is less than 1, the system is said to be underdamped. Again, I've color-coded the terms in the equation here. The decaying exponential term looks like this. The two complex exponential terms combine to a sinusoidal signal that looks like this. When we multiply these two signals together, we get a sinusoid that dies out with time. More specifically, underdamped system natural responses are exponentially decaying sinusoids. The exponential bounds the amplitude of the sinusoid. Underdamped system responses can oscillate and overshoot, unlike the overdamped and critically damped system responses. For underdamped systems, increasing the damping ratio reduces the amplitude of the overshoot and reduces the time required for the oscillations to die out. Finally, let's compare the responses of all three types of systems. The black lines are underdamped system responses. These responses can oscillate. The critically damped response, shown in blue, doesn't oscillate. Overdamped responses, indicated in red, don't oscillate, but they can respond slowly if the damping ratio is high. The overall trend is that damping ratio increases in this direction. All of these responses are for systems that have the same natural frequency. In general, increasing the natural frequency at a specific damping ratio will cause the system to respond more rapidly. These trends are important since they allow us to perform system design. Many design requirements are stated in terms of how rapidly the system has to decay and what the maximum allowable overshoot can be. There is an exception to the overshoot rule relative to overdamped and critically damped systems. Under certain circumstances, these systems can overshoot once, but only once. The typical shape is shown here. The response can cross the x-axis once and then approach the final value from the bottom. Increasing the damping ratio reduces the amount of overshoot. In order for a critically damped or overdamped system to overshoot its final value, the initial condition on the slope of the response, y dot sub 0, must be non-zero. You can see that in these examples, the initial condition on slope is large and negative. Finally, I want to mention why it's important to understand these categories of responses and the effect that the damping ratio and the natural frequency have on the response. If we have the differential equation and the initial conditions, we can solve the equation to determine the response without knowing anything about natural frequency or damping ratio trends. However, knowing the effect of zeta and omega n on the response means that we can estimate the response and perform valuable sanity checks on our solutions. More importantly, knowing these trends helps with system design. In many ways, the design process is the opposite of analysis. Unlike analysis, in design we're often given requirements for a desired response, and we need to create a physical system that provides that response. In design, we need to use the requirements to estimate the damping ratio and natural frequency of the system. Those parameters, in turn, dictate the terms in the differential equation governing the system. Since the terms in the differential equation correspond to specific resistor, capacitor, and inductor values in a circuit, we can use those terms to create a circuit that has the appropriate governing differential equation and thus the required overshoot and response time. Now that we've gotten an idea of the effect of the damping ratio and the natural frequency on a system's response, we can use that knowledge to estimate the system's response and design systems that have a desired response.